Welcome to CSI Training. Here at CSI, we are seriously committed to helping you achieve your goals in your reliability-based maintenance programs using predictive and other proactive maintenance methods. Whether you've just been assigned to the vibration monitoring team or been a valuable player for many years, we're sure you will benefit from the tips and concepts presented in this program entitled Data Collection Techniques to enhance your abilities to obtain the most valuable data for trending and diagnosing machinery conditions. Some questions often asked are, why do we need to collect data so often? And why can't we just collect data when there appears to be a problem? These are the first questions we will answer. Other questions include, which is the best sensor to use? And where are the best data points on pumps, motors, gearboxes, belt-driven equipment, and pillow block bearings? All of these questions and more will be answered. The previous program, Introduction to Vibration Analysis, showed how the spectral and waveform data we acquire is a representation of energy actually occurring within the machine. This program builds on the previous program and shows how to get the best data that is an accurate representation of the energy actually occurring in the machine. By applying the information presented in this program, you will be able to acquire the best possible data that will aid in the machinery analysis. Although vibration monitoring has been done in various ways for many decades, it is only in the last few years that routine vibration monitoring has been widely used. With the advent of portable data collectors and PCs, came the ability to acquire and store spectral and waveform data. Vibration monitoring programs have proven effective in reducing overall costs for industrial plants. Since vibration monitoring can indicate the health of a machine, these predictive maintenance programs, or PDM programs, can prevent machinery damage and costly delays caused by unforeseen machinery failure. There are two concepts for monitoring equipment like this. The first is, only collect data when a problem is suspected, and at that time do an in-depth immediate analysis. The second concept is, monitor the machine on a periodic basis and trim the data for any change that would indicate a developing problem. Analyzing a machine only after a problem has been detected seems to be a logical, labor-saving concept. The drawback to this is we may never know there is a problem until a failure is imminent or has already occurred. The damage caused is often much more severe and costly to repair than problems corrected at an earlier stage. However, when a machine is routinely monitored on a periodic basis, variances in the data indicate changes in the machine. These changes can be analyzed, and the problem can be determined, allowing ample time for ordering parts and scheduling a downtime. In summary, routine periodic data collection and analysis yields increased uptime, decreased maintenance and repair costs, increased lead time, as well as a trend useful for determining machinery life expectancy. To maximize the benefit of collecting this data, especially trending, certain conditions must be met. The data must be collected at the same locations, in the same way, using the same sensor type and the same sensor mounting. The general rule of thumb is, acquire 2 radial readings per bearing location, and at least 1 axial per shaft. The radial reading should typically be the horizontal direction and the vertical direction. These radial readings will give the analyst an idea of how the machine is moving up and down, as well as side to side. For horizontal machinery such as this, where the mounting is at the bottom, we typically would expect less movement up and down because it is limited by the mounting. The analyst compares these vertical readings to the horizontal readings to check for problems, such as a soft foot condition or loose mounts. An axial reading is one which is the same direction as the shaft or axis. In this motor, the axial measurement could be made at either end. We use the axial measurement to indicate how much the shaft is moving from end to end. Theoretically, the readings at one end should be the same as the other, since the same shaft extends the length of the motor. Actually, the readings will vary some from end to end, due to possible differences in mounting positions and the physical design of the machine. So in order to get the most useful data for trending and routine analysis for each machinery component, collect a horizontal and vertical reading at each bearing location and at least one axial reading per shaft. Some suggestions should be made regarding the location of collection data points. A previous section identified the need for horizontal and vertical measurement at each bearing location, as well as at least one axial measurement per shaft. The magnet with two poles can be used on a wide variety of surfaces. If the machine has a smooth area, such as this one has, the magnet mount can be placed directly on it. The outboard end of this motor poses a special problem. The only smooth area is on this fan cover. Using its surface for mounting does not give an accurate picture of the motor vibration, but simply the energy of the cover, which may be transmitting only a very small portion of the actual machine vibration through it. With the cover removed, we can get a better idea of what we are trying to achieve. This is the fan, and the bearing we need to monitor is further inboard, here. The best reading could be achieved by removing the fan cover and placing the sensor on the casting near the bearing. Obviously, this is not an option, since the cover must be in place while the data is acquired. The alternative is to collect data through this area of the motor. With these cooling fins spaced closely together, it becomes necessary to place the magnet mount on the fins. It could be placed across the fins or in line with them if the magnet's two poles will line up. For routine data collection, remember that we may not be able to take the time to get the best location, but that the data should be repeatable. This makes trending a valuable asset to the analyst. Although the horizontal measurement could be made on either side and provide good information, it is best to maintain the same horizontal measurement orientation from one routine survey to the next. The analysis equipment is so precise that even minute differences from one side to the other can significantly alter the data. The best place for an axial measurement is near the shaft center and on the bearing in the load zone. The load zone is the radial direction the most force is applied during normal operation. In horizontal machines, this is usually in a clock face position of 4 to 5 o'clock or 7 to 8 o'clock, depending on the direction of rotation. The axial measurement on this motor could be made at any of several places. The simplest place is on the end bell at the recommended clock face position, but the same restrictions apply for this axial measurement as for the radial measurements. Don't make measurements on the end bell, as it will only be an accurate indication of the bell's movement, not the machine's movement. If no better place is available, the axial reading could be made on a through bolt that fastens the end bell to a solid part of the motor. Be sure the bolt is tight. Long bolts may have resonant frequencies that substantially reduce the linear response range of the sensor. Another usable location is the lift hook. If the lift hook is simply a loop, be sure to make the measurement at the base of the hook. If the lift hook is an integral part of the housing and of substantial size, it could be used and still obtain reliable data. Be sure the sensor is pointed in the true axial direction. The motor foot provides another location for the axial reading. If it is used for the axial measurement, the analyst needs to keep this in mind when analyzing the data. Because the foot is firmly fastened, any axial movement will be minimal. An axial reading on the lift hook would have more freedom to move and thus would have much higher levels of energy. When comparing amplitudes for radial versus axial readings, keep this in mind. Never use the electrical junction box for an axial measurement, even when it is a heavy casting of the motor housing. Data taken here will have higher levels of electrically related frequencies that may indicate motor problems that don't really exist. On the pump, the horizontal measurements should be made on this flange because the bearing is mounted directly in line here. Be sure the sensor does not cross the joint, which may cause it to rock and generate erroneous frequencies. The center section of these pumps is hollow, and measurements should not be made here, as the signals will not be accurate. The outboard bearing is located in this area, and the horizontal readings should be made here. Axial measurements could be made at either end of the pump, but the impeller end tends to show energy due to flow, which can mask other problems. The same criteria apply to vertical mounted pumps and motors. 2 radial readings at each bearing location and at least 1 axial reading per shaft. The radial readings should still be 90 degrees apart, but should be called X and Y direction. Machines that use pillow block bearings require another measurement to accurately diagnose certain problems. There should still be 2 radial measurements per bearing, but an additional axial measurement should be made on each bearing. Since the pillow blocks are independently mounted, it is common for them to be cocked on the shaft. The axial measurement is a good indicator of this problem, as well as early bearing wear due to heavy axial thrust. Pillow block bearings on shafts like this may be inaccessible due to guards, covers, or simply be out of safe reach. If the guard is mesh, the long stinger may be used to reach through it for the radial measurements. Although the stinger or long probe does not provide the best data, it is still far better than no data. However, it is important to collect an axial measurement on each pillow block bearing, and the guards or covers often prevent that. A better way to measure the covered pillow block bearings is to install a hatch door so that a magnet mount sensor can be used. The linear frequency range will be increased substantially to be sure to catch bearing degradation. Oftentimes, the pillow block bearing has rounded surfaces that cause the magnet-mounted sensors to rock. In cases like this, it is better to install a mounting pad for the sensor. The best way to measure guarded pillow block bearings is to install permanent sensors at the measurement locations. These sensors are then wired into a panel that has terminals for BNC cable connections. The measurements can be made without compromising safety or data quality. Remember that in most instances, the analyzer will be providing power to these sensors and that the sensor receives an electrical shock and requires a 3 to 5 second settling time. Belt-driven equipment has special considerations for selecting the measurement locations. Although the common rule of 2 radial readings and 1 axial per shaft still applies, it is the orientation of the radial readings that varies depending on machine design. When the center lines of the motor and driven equipment are in the same horizontal plane, there is no change in the measurement locations. When the shaft center lines are not in the same horizontal plane, 1 radial measurement should be made in line with the centers of both shafts, and the other should be 90 degrees to it. This inline measurement is also the direction of belt tension and is used to indicate eccentricity or excessive runout in the sheave as well as a bent shaft. The perpendicular or 90-degree measurement better determines sheave misalignment and belt resonance. It is important to acquire good axial measurements to confirm misaligned or bent sheaves. The same recommendations should be followed for these axial measurements as axial measurements on any other machine. Although the next video program in this series discusses gearboxes in depth, here we will cover the best measurement locations for them. Gearboxes have high-frequency occurrences that require exceptional data collection for proper analysis. Routine surveys for single reduction parallel shaft gearboxes require a minimum of 1 radial and 1 axial measurement at each bearing location. Use 2 radial measurements when troubleshooting problems in a gearbox. The extremely high frequencies associated with gearboxes may necessitate 2 measurements being made for each sensor location. 1 measurement would be low frequency, high resolution for detection of balance, looseness, misalignment, and bearing problems. The other reading would be very high frequency to 3 or more times the gear mesh frequency with high resolution for determining gear condition. The direction of radial measurements should be in the line of force of the gears, through the center line of the shafts. As in other measurements, we need to be as close as possible to the source of the energy with a solid transmission path through a web or internal frame to the measurement location, and as close as possible to the bearings actually supporting the gears. For multiple reduction and angle gearboxes, 2 radial measurements should be made at each bearing location as well as the axial measurement. This second radial measurement should be perpendicular to the first measurement. In order to get the best data, we need to understand some facts and limitations of the various sensors. Each of these sensors or transducers has distinctive characteristics that may make it more desirable than another for a specific application. All of these transducers are either piezoelectric velocity transducers or accelerometers. Their size, sensitivity, and linear frequency range are the primary differences. Here, we will focus on accelerometers. Inside these accelerometers is a piezoelectric crystal. This means the crystal is under pressure, and when an electric current is applied, the output voltage changes with a change in pressure. The change in pressure is produced by the vibration of a machine impacting the sensor. The analyzer reads this voltage output and stores it as your data. Because of the orientation of the piezoelectric crystal in the sensor, it is very directional. Typically, 95% of all the energy the sensor picks up is directly in line with the sensor. Only 5% of the vibration data is from a lateral direction. Because the transducer's sensitivity is very directional, it is important to get the data that will be of most benefit. In this machine, as well as most machines, we are interested in the energy generated by the rotating shaft. The rotating shaft transmits the energy due to misalignment, unbalance, bearing failures, and other faults to the casing. The sensor should be pointed directly to the center line of the shaft in order to pick up the most information from rotational energy. In order for the energy to get from the shaft to the sensor, there must be a good solid path to the sensor. The cover on the inboard end of this motor has reinforcing vanes molded into the casting. These will transmit energy from the bearing location to the sensor with little loss. However, the places without the reinforcing vanes are voids, and the energy is not transmitted as well to these locations. If you know the internal structure of the machine, collect the data where there will be a good solid path to the transducer. We need to use the characteristics of the sensor to maximize our results. Other limitations are built into the transducers that affect our data. One of these limitations is the linear frequency response range. Sensors are designed to function well in certain frequency ranges. This spectrum from a sensor mounted on a shaker table shows its linear or stable frequency range to be from approximately 2 Hertz to 10,000 Hertz. Frequencies below 2 Hertz or above 10,000 Hertz would not be accurate in amplitude. Another sensor must be used that is linear in those ranges for amplitude accuracy. Although a sensor is designed to perform well within its stated frequency ranges, there are resonant frequencies unique to the method of mounting the sensor that greatly affects its linear response range. A resonant frequency is a frequency that an object likes to vibrate at. Every object has at least one resonant frequency. When this tuning fork is struck, it will vibrate at a frequency that is dictated by its design. 3 design factors affect the resonant frequency of this tuning fork or any object. These factors are stiffness, mass, and damping. Increasing stiffness raises the resonant frequency. On the other hand, the frequency can be lowered by increasing mass. Finally, adding damping reduces the amplitude with little frequency change. The effect of resonance on your data is vibration frequencies that occur in the resonant frequency range of the transducer will be amplified by as much as 20 times. Therefore, it is important to know the limitations of the selected transducer and the manner in which it is mounted. This long stinger or probe is useful for reaching hard-to-get places and for reaching through a mesh guard to a bearing. However, this probe should not be used for general points because of the amplitude inaccuracies beyond its resonant frequency, which is approximately 300 Hertz. Since many problems you want to detect occur outside this frequency range, it is not the ideal tool to be used with a sensor. This 2-inch stinger is also a very handy tool and may be part of the standard accessory kit with your analyzer. It is handy because it allows places to be reached that could not be accessed with a magnet or other mount. The linear range of the sensor with this 2-inch probe is approximately 500 Hertz. This would be suitable for many machines that have shaft turning speeds ranging from 1,000 RPM to 1,800 RPM. This magnet has a powerful grip and two bevel bars or poles that will fit well on most flat or rounded surfaces. Using this magnet increases the linear frequencies of the same accelerometer to 1100 hertz. Therefore, it can be used acceptably on shaft speeds to 3600 or 5000 RPM and acquire the data you need. This small magnet has a flat surface for mounting. To avoid erroneous data due to unstable mounting, it should be used only on flat surfaces. The linear range of the same sensor with this magnet mount increases to 1600 hertz and makes it even more desirable if the mounting surfaces are flat. There are instances when even this frequency range is not high enough. When a coupling fluid is used between the sensor and the magnet and machine, the linear response range is increased in this accelerometer to 5000 hertz with less than a 10% variance. Typical couplant fluids can be a light oil or grease or even petroleum jelly. All of these magnets provide a greater frequency response range than either the 8-inch Stinger or the 2-inch Stinger. Another benefit of the magnets over the Stingers is they hold themselves on with the same force time after time to give you greater repeatability for your data month after month. Studies have shown that data varies substantially depending on the pressure used with a Stinger. When data is collected by different personnel, the data varies even more, which makes trending data risky at best. For this reason, it is often difficult to get good repeatable data with handheld mountings. This Quick Connect sensor mounting has the benefit of being placed at exactly the same location from one survey to the next, and it goes in place quickly. The response curve is linear over a longer frequency range and even exceeds the magnet mounts. Another method of mounting sensors is to stud mount the sensor in a pre-drilled, pre-tapped hole. This mounting method provides the greatest linear response range and will give the best, most accurate, repeatable data. Whether your sensor mounting is a Stinger, magnet, Quick Connect, or stud mount, collect your data using the same sensor type, the same sensor mounting, and the same locations time after time. When the locations have been selected for the data collection points, they should be marked to ensure repeatability of data. One common way to mark a machine for use with the CSI Model 908 or the 906 two-pole magnets is to use a paint marker to draw a target. A single line around the perimeter of the magnet location is usually adequate. It's not necessary to paint the target area solid. An outline is good enough. A fully painted target simply adds more damping between the sensor and the source of the vibration and reduces the amount of energy that reaches the sensor. You will find that after several uses, the paint begins to chip off due to the impact of the magnet as it is applied and removed. Another common method of marking the points is to glue on steel pads of the approximate size of the magnet footprint. When using the sensor with a smaller round magnet, such as the CSI Model 905A rare earth magnet, other considerations must be made. The contact surface of this magnet is approximately 3/4 inch in diameter and is flat. It should be used on flat surfaces only to avoid rocking motions that will make the data erroneous. To accommodate the flat finish of the magnet, a 3/4 inch diameter disc could be mounted to the machine surface with adhesive. When selecting an adhesive, there are considerations that must be made. The first is durability. It should hold to most surfaces well without losing its grip over time. It should be resistant to oils, temperature changes, and process chemicals. The second consideration is transmissibility. Does the adhesive transmit the energy through it to the sensor, or is some energy absorbed or damped out? Too much damping will cause high frequencies to be unnoticed. Since most severe problems show up in the high frequencies, damped signals could have a detrimental effect on your vibration monitoring program. CSI has done extensive research on adhesives and has included a good adhesive in the CSI Model 912 AccuTrend mounting pad kit. The kit includes 500 discs or mounting pads, adhesive, paint markers, and special accelerometers and magnets. The discs are machined of 410 stainless steel which has magnetic qualities and are engineered especially for use in industrial vibration monitoring programs. Because the linear frequency response range is greater for quick connect mounting than magnetic mounting, there may be equipment that warrants the extra time to mount these pads and use the quick connect fitting. The pad can be stud mounted using a 1/4 inch by 28 threaded stud, or it can be glued in place. After the quick connect pads are installed, the data collection is simple and produces a good high-frequency response range suitable for capturing gear mesh and other high frequencies within the transducer frequency range. A common method for marking machinery when a stinger is to be used is to paint a 0 at the measurement point location. By leaving the center of the circle open, there will not be a signal loss due to the damping effects of another layer of paint. Ensure repeatability of your data collection by marking the machinery. Whether you use a stinger or magnet mounting, mark the machinery with either paint or mounting pads suitable for your sensor mounting. When using the mounting pads, be sure the adhesive does not damp the signal. Routinely measure these same locations to enhance your trending capabilities. With the predefined routes of machines and measurement loaded in the analyzer and the machines marked, data collection will progress quickly. However, there are certain cautions and considerations that should be made to ensure the data acquired is good. The first consideration is to view the data live as it is collected. This will allow you to make a quick check that the data looks reasonable, and you may be able to diagnose problems as you collect the data. Some data collectors or analyzers, such as the CSI Model 2115, allow you to select whether to display the waveform, the spectrum, toggle between waveform and spectrum from sample to sample, or to display both the spectrum and waveform on a split screen. Select the display that benefits you most. The next consideration is the settling time of a sensor. When a sensor, especially a magnet-mounted one, is placed on a machine, it tends to smack the machine and shock the sensor. Let's look at this as the next point is taken. Many G's are imparted into the sensor as it is placed on the machine. This causes extreme amplitudes and will take 3 to 5 seconds for the levels to settle down. If this energy is included in the spectral averages for the measurement point, the data will be corrupted and of no value to the analyst. The same consideration needs to be made when powering a permanently installed sensor from the panel. Each time a powered cable is connected to the sensor, the voltage shocks the sensor in much the same way and requires the same settling time. Be sure to allow 3 to 5 seconds settling time after placing the sensor on the machine or connecting a powered cable to a permanently installed sensor. Another common data corrupter is the effects of triboelectric noise. All this means is slight movements of the cable during data collection produce changes in the way signals travel through the cable, and these changes are magnified by the signal processing. Let's look at the effect of cable movement during data collection. Notice the sudden rise in energy at the low-frequency end of the spectrum. This is often referred to as a ski slope because of its shape, but is commonly due to triboelectric noise or cable movement. The ski slope is especially common when data is acquired with a stinger because of the slight continual movement of the hand and cable. During data collection, be sure to avoid cable movement, as that may add a ski slope to your data, causing unusually high readings. Loose connections between the analyzer and the sensor will cause either erroneous data or no data to be collected. Bad data is recognizable at least 3 different ways. The simplest is to pay attention to the displayed message after each point has been collected. If the message is bad reading, then stop to determine where the problem may be. The bad reading message is triggered by the value specified for the valid range of the sensor. The validity limits for the sensor are set in the measurement point definition. The limits can be set for the upper and lower limits. Remember that these limits are the output units of the transducer, such as displacement, velocity, and acceleration. It is best to set the lower limit above the value recorded by the analyzer when no cable is attached, but below any levels expected for the measurement point. Usually 0.003 for velocity measurements is appropriate. Make the second check when a measurement point is complete. Look at the status and compare the overall value to the previous reading. The overall value for the previous reading is also displayed on the screen. If there is much disparity between the two overall values and you are confident no work has been done on the machine, then make the third check by viewing the spectral and waveform data, again looking for disparities. If any hardware connections are loose or the cable is bad, the signal may be intermittent, causing discontinuities in the waveform data. This waveform is typical of data that has gaps or discontinuities due to an intermittent signal. To increase the effectiveness of your data collection, follow these helpful hints. First, view the data in live display as it is collected. Secondly, be sure to allow settling time for the sensor after placing it on the measurement point. Third, avoid triboelectric noise by keeping the cable still. This will help avoid the ski slope on data due to cable movement. Last, check for loose connections or bad cabling by comparing the present reading with the previous one, checking for the bad reading message, and checking discontinuities in the waveform. There are certain key steps to do when an alarm is triggered. First, determine which frequency range or ranges are in alarm by pressing the page key and view the listing of the parameters. The alarmed parameters will be highlighted. Press the page key again to display the spectrum and make note of the frequency ranges that alarmed. View the waveform to confirm any possible preliminary diagnosis. Next, acquire another spectrum with higher resolution and perhaps focusing on the frequency ranges that alarmed. This high resolution will help pinpoint the source of the problems by separating combined peaks into discrete frequencies. After viewing this new data, be sure to store it so it will not be erased when the next measurement is made. This new data may be the key to a correct diagnosis. It may be helpful to set the analyzer in the monitor mode to continuously update the display and check other places on the machine to compare and narrow the problem to a specific area. Use this monitoring mode to measure places on the machine that are not routine point locations. If a problem area is detected, acquire a spectrum and store it, making note of any location or peculiarities. The third step is to visually inspect the machine, checking for obvious problems such as leaking lubricants, leaking seals, broken or loose mounting bolts, shims slipped out from the feet, and broken or loose components. If gauges are available, are they in the normal range? Be sure to record any observations to help eliminate questions when analyzing the data in the office. Some analyzers have the ability to store notes, and they will be transferred to the computer along with the spectral and waveform data. To summarize, when an alarm is triggered, verify that the data looks accurate and acquire a high-resolution spectrum to store with the point. The monitor mode is useful to check other parts of the machine. Be sure to visually inspect the machine for obvious or potential problems and record notes of findings or preliminary diagnosis. When measurement points are out of reach or are unsafe for personnel because of temperature extremes or environmental considerations, they can often be accessed by using the fiberglass extension pole with a strong magnet mount, such as the CSI 906 or 908 super magnet on the sensor. Using the steel mounting pad as a target helps ensure a firm mounting and good data. The swivel head of the extension pole adjusts for nearly any angle. Sensor grips are available for most common size sensors. All the measurement points that require the extension pole could be placed in one route to avoid the loss of time for changing the sensor and cabling. In the nuclear industry, measurements can be made on radioactive machines and minimize your exposure to radiation by using the extension pole. The ALARA considerations of keeping your radiation exposure as low as reasonably achievable are enhanced because the exposure is reduced exponentially by increasing the distance. Tripling the distance cubes the reduction to radiation exposure. Oftentimes, the full dress is reduced to extremity protection because of the ability to extend your reach and reducing radiation exposure. As we have seen, there is much more to data collection than just placing a sensor on a machine and expecting a complete and comprehensive diagnosis. To acquire the best data for the most complete diagnosis, we need to know the limitations of the sensor, determine the measurement locations that provide the best path of transmission, and mark the machinery to ensure repeatability. During data collection, allow for settling time and avoid cable movement. When an alarm is triggered, collect high-resolution data and take notes of any observances. Never leave in the field what you may need in the office. Thank you for selecting CSI for your technology and product-specific training needs. We look forward to assisting you in your future endeavors.
For information on these or other CSI training videos, books, manuals, posters, or classes, call area code 615-675-2400, extension 237. CSI Training offers state-of-the-art benchmark training for 28 different courses, more than 200 times a year in Knoxville, Houston, regionally and internationally, on topics including single and multi-channel vibration analysis, slow speed analysis, oil analysis, thermography, acoustic analysis, as well as product-specific classes. Other courses include correction technologies such as alignment and balancing and root cause failure topics. CSI Training is also recognized as the leader in industry certification, offering multi-level development and certification paths for various crafts and skills in the PDM and RBM fields.